5.2 continues with this example. According to this USA snapshot, 75% of Americans know someone has become addicted to a drug other than alcohol. Suppose we randomly select 15 Americans from the population. Does X, the number of people in our sample who know someone has become addicted to a drug other than alcohol, follow a binomial distribution? So, in order for us to have a binomial, first thing, we need to be counting up successes. So here we're talking about the number of people who know someone has become addicted to a drug. So that number is a really key word to say, hey, we're doing a count. This is probably a binomial. And this is just a heads up for future questions when we have lots of different options available to us. So in order to have a binomial, we need to be able to find all those pieces we talked about in the last one. I'm going to give you a little mnemonic device sort of to remember this, or acronym. The four things we need in order to do this binomial is we need bins. And this is something a fellow TA came up with at SDSU and I still use. B is that we need our binary outcomes. Right? We need our success and our failure. So in this case, our success, the things that we are counting, is this knowing someone who's become addicted to a drug other than alcohol. So we'll say knowing an addict. Right? And then failure, well, that's just the opposite. It's not knowing. The I here is for independent. So in this case, we have our binary outcomes, knowing and not knowing. That works. Independent means that one person or one trial of people in this particular thing or in our sample or whatever we're doing doesn't influence the next person. So if first person knows someone who's become addicted to a drug other than alcohol, this doesn't influence the probability of the next person. And this is also good because of the fact that we are doing a random selection. So the random selection is what gives us our independence. So as soon as we have that, we can check off independence. In the bins formula is just what is our sample size, what is our number of trials, our number of observations. So here we have 15. This is important because remember, we need a fixed number of trials. We can't be pulling people until we get to a certain number. We need to say we're pulling 15 people. Let's talk about the number of people who know someone. So this is also good. All right, and the last one, the S in this little device is that success stays the same. Remember that probability of success, our P has to be the same for each person in our trial. So in this case, our P, oh goodness gracious, that's wrong. Our P is equal to, 75% of Americans know someone has become addicted to a drug. So that probability of success should be 0.75 every single time. No reason it would change when we're randomly selecting people. And then Q, our probability of failure, is just 1 minus that. If 75% of people know someone who's been addicted to a drug other than alcohol, 25% of people don't. And now we can see the questions that come next. Now that we can confirm, after all this bin stuff, that we indeed have that the count of the number of people out of these 15 that know someone who's become addicted to a drug other than alcohol follows a binomial with an N of 15 and a P of 0.75. Now that we've confirmed that, we can use the sweet formula from the last page. So here are the 3 types of questions that you can really see after this on the test. So first question says, let's find the probability that exactly 6 of the 15 Americans know somebody who's become addicted. So we're saying the probability that our number is exactly 6, right? That our count of successes is exactly 6. This is exactly like the formula on the last page. This is when I can go ahead and grab that formula, which was right here. You guys can go back and look at it, this formula, and say, okay, let me translate everything I have. So that formula says, first, I'll just rewrite the formula as it is, and then we'll replace each of the pieces. So N choose K, P to the K, Q to the N minus K. So I'm just going to go ahead and replace each piece. When we figured out if this was binomial or not, decided our N was 15. So I can replace both the N's with 15s. We decided then our K is just the thing that we're looking for. So in this case, I can replace every k with that 6 that we want. And then the last thing to replace is our P and our Q. We know our probability of success, this is 0.75, and our probability of failure is 0.25. So that's what I want to type in my calculator. 15 choose 6, and then 0.75 to the 6th, and 0.25 to the, what is 15 minus 6 to the 9th, to all the leftovers. All right, so let's go to our calculator really quick and try this thing out. Okay, so we need 15. Remember, we got to type that in first. Go over and get our NCR button. 6. If we want, we can press enter right now to get that number. There were 5,005 ways to order 6 successes in those 15 slots. Thank God we have this button, right? This is going to be times 0.75, 0.75 to the 6th times 0.25 to the, and then your, by the way, your caret button lets you do exponents to the 9th. Press enter, we get that the probability of this is 0.0034. So this whole thing is 0.0034. Now that's not the only way this question can go. That's the easiest way, where it just says, hey, plug in, we've given you the number, all you gotta do is type everything in, which is challenging enough the first couple times. But sometimes we're not interested in just one outcome. We want to know about multiple outcomes at once, and that's what you see in the next question. The next question says, find the probability that at least 14 of the 15. This isn't saying exactly 14. Now there's a direction. And this is where you need to either know your translations for inequalities really well. So you could actually do this. Well, the probability that our number of successes, well, I know at least means a greater than or equal to. You could do this. To me, that's not terribly helpful. I am a visual person. So what I like to do is I like to kind of do that, the table almost that we had done in that previous example, the one with this one, where I have all the outcomes. So if somebody says, what's the probability of at least 2? I know that's 2 or more. I like that a lot better. For me, it's just more visual. I can kind of see what's going on. So how I do that in these questions is I make myself a baby table. I say, okay, well, what are the possibilities? If I'm selecting 15 people, that means I could have none of them know someone all the way up to all of them knowing someone. None to all. That's how this works, right? So every possibility is in there up until those ones. And then it's just easier in my brain to think, okay, at least 14, that's like being at least 21 to go to the bar. So they could be 14, but it could be more. These are the 2 outcomes I'm interested in. So if I'm doing this problem, this is the probability that x is equal to 14 or x is equal to 15. And remember, these things are all mutually exclusive or disjoint. If I had my table, I would just add up those probabilities. So that's all I'm going to do right here. I'm essentially using the disjoint rule for or without really thinking about it. So I would need to do 2 of these formulas, one with an n of 14 and one with an n of 15. And then plus 15 choose, and then do the same thing with the 15. So that's what I would need to be typing into my calculator. Now, you can be a little more clever here. You don't, if you know a little bit about these combinations, or just think about what we had done before. This particular one, 15 choose 14 is just going to be 15. This is getting everyone but one person, so that's sort of like how many people are we selecting. So you can simplify this up a little bit before you go to the next page. 15 choose 15, that's everyone, that's all. There's no other way to order. This is actually just going to be equal to 1. But again, there's no reason to be to have to use anything clever, this is also going to equal 1. You can just type these into your calculator and let your calculator do the work for you. So I'll try this out again. Try this out again in the calculator. So I would do these separately. If I didn't realize those shortcuts, I would do 15, choose 14. Oh, it's 15 times 0.75 to the 14 times 0.25. And again, I realize the 1 isn't necessary, but you can just type it exactly as you see it. So we got that probability, 0.0068, and we do the same thing for the other one. 15, again, I could, if I didn't realize it, it doesn't matter. I can just do the work exactly as it looks, times 0.75 to the 15. And again, I know it's silly, but I could just type it in exactly like it looks like. So we have 0.0668 and 0.10134. So this is 0.0668 plus 0.0134. If we add those together, I did not type those into my calculator correctly. All right, we get 0.0802. All right. And our last one here, the probability that not all of the 15, this is when I want you guys to take a moment, pause the video, figure out what math you'd be doing. All right, so if you're coming back, you could have done this a number of ways. I, again, like my visual. All would be all 15, right? Just like I said before, which means not all is everything else. Now, that would be silly to do this as the probability of x equals 0 plus the probability of x equals 1. This would suck, right? So what we're going to do is essentially like the questions about the iPhone or rebooting that we saw in the homework and the notes for 4.5. We're going to say the probability of not all is just 1 minus the probability of all, right? That's 1 minus the probability that x is equal to 15. Now I could use the formula here, but we've already found this probability, right? We did that here, here, here. So I'm just going to do a 1 minus 0.0134, which gives me 0.9866. I hope, because I did not use a calculator. We have one last piece here. We're going to redo those 3 questions because there's an even sweeter calculator shortcut than that combinations formula. So if you want to see the really sweet calculator shortcut, watch the next video and I'll run you through it.